So hello everyone, and thanks for joining to today's workshop on open source battery modeling, which is hosted by University of Waterloo Electrochemical Society, or WatECS for short. So WatECS has hosted and continues to host workshops with the aim of providing interesting, diverse, and relevant content on the field of electrochemistry. For more information about our previous and upcoming events, please visit our website at watecs.ca or join us or follow us on social media. So now let's just move on to today's event. For today's event, I'm excited and honored to have Robert Timms, who's a core developer at PyBaMM, and the team at BatteryDev, which includes Paul Gasper, Joachim Schaefer, and Anushka Bhutani. So just to simulation using electrochemical, thermal, and various battery degradation models. While BatteryDev hosts hackathons on various battery, data science, and machine learning projects. So before going into the presentation, just a little brief about the event format. So first, we will have a presentation from Robert Timms on PyBaMM, which will be followed by a presentation from the team at BatteryDev, and the event will be concluded with the question and answer session. So the audience members are encouraged to leave their questions in the chat box during the presentation, and they will be asked if we have time during the Q&A session at the end. Another note is that this event is being recorded and the recording will be available on our website and YouTube channel. And for all the chemical engineering graduate student at University of Waterloo, please note that this event can be counted as your degree seminar attendance. So please stay tuned till the end of this event, and the online code will be available in the chat box about 10 to 15 minutes prior to the end of this event. So without any further ado, let's go into the presentation. So first, it's Robert Timms.
Cool, great. Yeah, thanks very much for having me along to this session. I'll just get my screen up for you. Cool, so hopefully you can see my slides coming up there. Yeah, I'm Robert Timms. I'm currently a postdoc at the University of Oxford in the UK, working on battery modelling. And yeah, part of what I've been doing has been helping to develop this open source battery modelling platform, PyBaMM, which some of you may or may not be aware of already. And sort of over the next 20 minutes or so, I'll hopefully give you an introduction as to what PyBaMM is and what it can do and why we wanted to set it up in the first place. And then I'll finish up with some examples of some things that people have used PyBaMM to do. But yeah, before I get started, so PyBaMM is this sort of big open source battery modeling platform. We've got lots of different contributors, but it was sort of originally started out with some core developers at the University of Oxford. Some of them moved on now to places like Carnegie Mellon, but these sort of institutions here are hosting the sort of lead developers of the project, and it's funded in part by the Faraday Institution, which is a UK body funding lots of battery modelling research. But you know, we've got contributors from all around the world now, and I'll say more about that as we move on to the next few slides. Cool. So what is PyBaMM? So really, we set up PyBaMM to be this open source framework to enable collaboration across different institutions and across different nations, with the overall goal of accelerating battery modeling research. So when I'm talking about battery modeling here in the context of PyBaMM, I'm thinking about sort of physics-based battery models where we're writing down, you know, partial differential equation to try and describe what's going on within a cell. And what we found really is that, you know, if you're a battery modeling PhD student or postdoc or whatever, you come along and you seen probably DFN or Newman's model for the first time, and you go away and you start coding that up from scratch, and everyone's got their own implementation of this particular model written in their own favorite platform and everything else, and you're kind of reinventing the wheel quite a lot. And actually what we wanted to do was to provide this framework where people could build on the research of others, and you can take pre-existing models and sort of chop and change them and add on the new physics that you're interested in. And so that was kind of the provide this framework that enabled that. But alongside providing the actual technical tools to implement these models and solve these models, we also thought it was a really great opportunity to start building a battery modeling community centered around this piece of software. And so there's kind of two parts to PyBAM. One part is the kind of the scientific and the capability part of providing these fast, reliable battery simulations, providing this platform where you can develop new models, build on existing models. But also it's about this community building aspect. And this community has grown really quite a lot since we first started in 2018. So we kind of started out building PyBAM with 4 or 5 of us starting to code up these models. And now we've got a really active research community. We've got over 40 different contributors from across the world, hundreds of users, and lots of participants came to our latest training workshop, for example. And we think the size of our community really speaks to the success of this project on the whole. And there's kind of a few benefits into having a kind of framework like this that's open source and widely available, and freely available. And first of all, hopefully it kind of makes battery modeling easier to do. That's our sort of primary goal with this, to lower the barriers to entry of developing and solving battery models numerically. But also it kind of builds trust in the kind of models that people are writing down and solving. Quite often there's this difficult transition from writing down a model in an academic setting and getting it used in industry. And sort of part of the difficulty of that transition is either um, difficulty understanding something, something perhaps isn't ready for industrial users, and it's not in the right setting, the right framework. And also there's a level of trust. Can an industry user or someone wants to use this model to do some kind of practical application trust what the model is doing and what it's saying? And hopefully by having this very transparent and open framework, we can really build trust in all the models, make people's research very easy to reproduce. You can write your paper, you can share your data, you can share your code. People can go away and play with your model and investigate it and see when it works, when it doesn't. And so hopefully all these things together just sort of build this really nice community, uh, improve the research that's going on, the quality of the research, and also help this research transition into an impactful sort of industry setting. And if you've not used PyBaMM before, or you want to come and check it out, there's a number of ways you can get involved with the project. One thing you can do is just try it online in your browser. So if you head over to our website, the link's just at the bottom of the screen there. And we've got lots of examples that you can just run straight in your web browser with no need to install. You obviously can install it. It's a Python-based package. You can install it via pip like you do any other Python package. And obviously, we've got GitHub there, so all of the development is managed via GitHub. So you can go over to the repo, look at all the code, look at open issues, use our discussion board, and so on. So lots of ways to get involved. So that's kind of the picture of why PyBaMM and why we went around to set this thing up. But what does it actually do? So we kind of view PyBaMM as a kind of virtual physics lab for exploring new battery modeling mechanisms, or new models of particular mechanisms rather. And also an environment where you can compare models, validate models, and understand the predictions that you're making. And a lot of this usability comes from the way physics is implemented within PyBaMM, or the way the equations are written down. And I'm going to talk more about that in a few slides' time. But essentially, everything in PyBaMM is built around this plug-and-play physics framework. So if you've got some particular physical mechanism you want to include in your model, you can just say, I want to model it in this way, and that's the model I'm going to choose. And I'll show you later on how you can collect together different models of different physics and start to build up a more complicated model to try and understand the system you're interested in. So that's kind of the key concept of PyBaMM. It's this flexible modeling framework. And you can use it to do all kinds of different things. So one of the things we were originally using PyBaMM for was comparing different models for accuracy and speed. So a lot of the work we were doing was deriving reduced order or simplified versions of different battery models. And we were trying to understand, when is this particular model valid? What parameter regime can I use it in? What's the kind of error I make when I use a simpler model versus a more complicated one? And what's the speed increase I get? How do I play this game of trading off computational complexity, speed, detail of my predictions? And PyBaMM's a really useful tool for doing that, because it's very easy to just add in these different models, compare them, and understand what's going on. All of this functionality is very, very good. But if it's not easy to use, then it's not as impactful as it could be. So we've also spent a very long time trying to wrap all of this functionality up in a really easy to use interface. And this is the goal of making it easy to use PyBaMM to do things like simulate an experimental protocol that you might do in the lab. So for example, at the bottom right here, we've just got an example of running a particular CCCV experiment. And in PyBaMM, you can just go away and you can write out in kind of plain English the experiment you want to run, and go away and PyBaMM will run that for you. And you can build up very, very complicated experiments using this kind of syntax, or equally, if you've got, say, a CSV file of time versus current data, you can load that in and simulate that like a drive cycle type situation. So there's lots of ways you can use all these models, and really, yeah, we just wanted to provide this framework, this box where you could package up all of the sort of academic research into this nice, easy to use interface. And then you can start using these codes and these models to do more practical things like investigate different designs of cells, do parameter optimization, and so on. And I'll talk more later on about this particular image in the top right-hand corner, where we used PyBaMM and coupled it together with another software package to investigate the design of a cylindrical cell. And this is an example of how you can use PyBaMM as a sort of plug-in to other software packages. So not only is PyBaMM providing a framework where you can do battery modeling research and use battery models for practical applications, it's also a tool that you can drop into other workflows and sort of more kind of systems level simulations. And I'll see an example of that towards the end of this presentation. So as I said, you sort of package up all of these battery models to enable people to run fast and reliable simulations via easy to use interface. I've already spoken about, defining experimental protocols. Here we've got an example of GITT, or providing drive cycle data. Or you might do things like test out different parameterizations, or parameterize a particular model against some experimental data you might have. This example on the left is from the paper by Ecker from 2015. And to give you a sort of ballpark figure of times, solving something like DFN is a couple of seconds on a normal laptop. And if you have a coarser discretization of that, you can reduce that solve time to order of milliseconds. So these are the reasonably fast simulations of relatively complex battery models. Okay, so how does this all work under the hood? I kind of talked a bit about the kind of the big picture of why I wanted to make PyBaMM and the kind of things it lets you do, and we'll see some more concrete examples later. But really, the flexibility of PyBaMM comes about from the way in which the models are set up, implemented, and solved. And so all the models that go into PyBaMM kind of go through this simulation pipeline depicted on the left. So if you want to use PyBaMM to write down a battery model, first of all, you write down your model in symbolic form. So you can just write out equations like you would a mathematical equation. So you can say, some quantity is divergence of gradient of some other quantity or whatever. So you can symbolically write all of your models, and we'll see later how you can write these as submodels and collect them all together. And then once you've got your model, your symbolic model, you can parameterize this model. So provide some values for the parameters, which might be constants, they might be functions. So you might have an open circuit voltage that depends on concentration and temperature. So you can pass these things into a particular model. So in this example on the left, I've got a diffusion equation, and I've got a diffusivity, and I said it's 2. After you've chosen your parameter values, you can pick how you're going to discretize this model. So I'm going to solve this thing numerically. I've got some partial differential equations or ordinary differential equations, and I need to choose how I'm going to solve this. And so not only does PyBaMM give you the kind of plug and play flexibility over the models, the physics you're including, and the parameter values you're going to use for that simulation, it also lets you choose how you're going to solve this thing, the numerical aspect of it. And so you can discretize your equations on some given geometry, on some given mesh, and this turns your partial differential equations into a whole bunch of ordinary differential equations with some matrix operations. And then after that, you need to go ahead and step this model forward in time somehow. So you can choose some algorithm for doing that. And again, you've got sort of a number of different choices of solvers that you can integrate within a PyBaMM model. And then once you've solved your model, there's a bunch of functionality for sort of post-processing, visualization, or you can kind of just dump all the data out and plot it and manipulate it using whatever is your favorite software for doing that. And so as I said before, this kind of pipeline framework makes it very easy to sort of compare different models, because I can just pass 2 different models into the same pipeline, parameterize them in the same way, solve them in the same way, and compare them like for like. So I'm not using one model implemented and solved by group A and another model implemented and solved by group B. And then when I compare these things, am I comparing the models, or am I comparing how they were implemented numerically? I can be certain that the thing I'm comparing is what's this model performing like against this other model. And then you can also do things like compare different parameterizations, or kind of wrap this kind of pipeline framework in some optimization routine to parameterize your model against some given data. And so this kind of framework is the thing that provides the flexibility of PyBaMM. And so the thing I think is the most valuable part of PyBaMM, in my opinion, is the sort of plug and play nature of the physics of the models themselves. So PyBaMM, as it stands, it ships with a kind of a comprehensive library of different models. So if you're familiar with these kind of physics-based battery models, these are things like Newman's model or DFN, or the single particle model or single particle model with electrolyte. And so, we ship with all these sort of standard models that you see in the literature. But actually, the way these models are constructed is that they're a collection of different submodels. So if I've got a single particle model of my cell, I might have some model that describes what's happening within that particle. I might have a model of what's happening in the electrolyte, a model of what's happening in a sort of thermal aspect. I've got a lumped thermal model, some distributed thermal model where I'm modeling the temperature distribution. Have I got side reactions, degradation, whatever else? And I can collect up all of these different submodels that I want to choose and bring them together to form my overall model. And the crucial aspect of that is that all of these different physical effects are fully coupled in the appropriate way. So you can start to understand the interactions between different physics, and that's particularly important if you want to include multiple degradation mechanisms in your model, because you can get all this sort of positive feedback of different degradation mechanisms interacting with one another. And the goal of this really is that if you take your model or your new model of some new mechanism of degradation or whatever else you like, if you implement that in PyBaMM, the goal really is that straight away you can then start using your model in conjunction with all the other models that already exist in PyBaMM. So you can say, if I add in some mechanical model of particle cracking or whatever else, straight away I hopefully can say, how does that interact with if I include a particular thermal model, or I change the description of my electrolyte or whatever else. And so you can really start benefiting from sort of the cumulative work of the whole research community when you start implementing your stuff in PyBaMM. And what this really lets you do ultimately is do things like predict cell performance and lifetime due to all this different coupled effects. And we've got some functionality in there that can let you track various different health metrics of your cell, like capacity fade and loss of active material, loss of lithium inventory, and so on. So hopefully all this degradation modeling is wrapped up in some nice, easy to use framework that lets you understand how your cell is going to degrade over time if I use some particular model to describe that and some parameterization of that. And there's a whole bunch of different physics included in PyBaMM. I won't list them all here, but you can go to our website and take a look. So what this means you can do is I can start implementing, I've got DFN and I add in some side reaction that might change the porosity, for example, and here's some plots showing that. So that's kind of what PyBaMM is. I just want to spend the last sort of 5 minutes or so just quickly showing some examples of the kind of things people are using PyBaMM for, and also set out the kind of different areas that we're working on within PyBaMM as sort of a core development team, and the things we're sort of interested in. So primarily, the main focus of PyBaMM is providing this robust framework for doing science. So I've listed sort of 4 areas of interest here: science, solvers, interfaces, and packs. And sort of the sort of core principle of PyBaMM is integrating all these models, this science. But also along with that, we're thinking of solvers, and by that I kind of mean the numerical aspect of things. So all the different integration techniques I can use to solve these models, different ways of discretizing models, and so on. So that's more of a numerical implementation thing. But obviously, if you can make your model faster to run or use less memory or whatever else, that's great. And so we're sort of very interested in that and welcome contributions in that area, as well as contributions of new models. We're also thinking about interfaces. So how can I get PyBaMM talking to other software? And this might be, if I want to drop PyBaMM into some, I don't know, CFD simulation that's doing some modeling of some complex liquid cooling system or something else. We could imagine PyBaMM not just being a standalone battery modeling tool, but a kind of drop-in replacement that can sit in with a systems level simulation. And we're also thinking about how we can extend to packs, and that might be via the interfaces route. So, I could use PyBaMM within some other software package that lets me, map out my pack, or maybe I can do something directly in Python to sort of bring PyBaMM up to the pack level rather than the single cell level. And so mostly I'm going to just show you some examples of science that people have done, and I'll talk a little bit about interfaces and packs too, but I won't say much about the numerical aspect of things. Cool. So I think I spoke already, about degradation modeling. This is a very important area of research and something that, is very important to understand if we're going to understand the lifetime of cells and how they're going to behave in a real application. And so a paper that came out very recently was a paper that coupled together numerous different degradation mechanisms within PyBaMM to try and understand how these different mechanisms interact with one another, and in particular understand, if I use my cell in a certain way or under certain operating conditions, how do these different degradation mechanisms like plating or SEI lead to different degradation modes, such as loss of active material or loss of lithium inventory. And is the way I use my cell, can I map a different path through this kind of degradation space? So, if I take this image on the left, what are all these different interactions that are happening and where do I end up? How does my cell die? And this is just one of the ways that this plug and play model gives you, the framework rather, gives you this flexibility to understand these kind of different paths through degradation space. So yeah, this particular paper is led by Simon O'Kane at Imperial, and it coupled together different mechanisms and showed these different pathways were very complicated and kind of depend on usage. And this has lots of potential useful outcomes for predicting lifetime, depending on how you're using your cell and trying to understand which degradation mechanisms might dominate in certain operating regimes. Something else that was implemented in PyBaMM is particle size distributions. So if you're familiar with these kind of models, typically we assume there's a single particle size in each electrode. But actually we could assume instead that we've got a distribution of different particle sizes in each electrode. And actually including this physics was able to explain or offer a possible explanation for kind of the slow voltage relaxation you see during rest phases of experiments. So here this image just shows in red the standard DFN and in blue dashed the DFN with a particle size distribution, and the grey line is the experiment, and you get a much better fit to this slow voltage relaxation. And this is again another great example of how extensible PyBaMM is. You can just implement a new model for what's happening within particles, and straight away that interacts with all the other submodels so that you can use the existing code for how the electrolyte behaves, temperature, everything else, and so on. So this is a really nice example of how you can just extend an existing model using the PyBaMM framework. Along the same theme, we've had recently some work, this paper led by Weilong I, about composite electrodes. So I've got electrodes with two different chemistries in, so a graphite and silicon composite, for example, and they extended PyBaMM to let you include multiple chemistries within a given electrode. And then you can understand things like, am I using one chemistry more than another at a certain state of charge? Does my cell usage or sort of the usage of particular chemistry in a given electrode depend on how deep my discharge is. And again, another nice example of the extensibility that the framework provides. The last few examples are talking about interfaces and packs. So this particular example was sort of some work done to see if we could use PyBaMM in conjunction with the software. And so in this work, we took an image of a jelly roll cell and use this CT scan to construct an equivalent circuit network describing all the connections between the current collectors and active material layers. And we use this sort of global equivalent circuit model for charge transport on the sort of length scale of the entire cell. But then locally, between a sort of pair of current collectors, we used a physics-based model in PyBaMM to describe what was happening in the electrochemical part of the model, so in the sort of electrodes and separators. And so here we kind of ended up coupling together, I can't remember the numbers now, but it's kind of like hundreds of single particle models or DFN models connected in a sort of larger equivalent circuit representation of the overall cell. And then we could do this, use this to do things like assess different designs where I've got different numbers of tabs or different tab placements, or a tabless design like the Tesla cell, and understand the effect that has on how uniformly a cell is used, or the effect on heat generation. And so that was a nice example of how PyBaMM can be used in conjunction with the software as a kind of plugin. And so my very final example is just talking about work we're doing on packs and extending PyBaMM to pack level. We've recently released an initial version of Lion Pack, and there's the URL for the GitHub repo there. And essentially, this is a pack modeling software that lets you arrange PyBaMM models in some pack configuration and then run that. And we're working with some collaborators at Oak Ridge National Lab to work on sort of parallelization of these massive pack simulations. But that's sort of a very early days in that package. That's a very new thing we've been working on, and it's under active development. So if you're interested in getting involved in that in particular, we welcome new contributions there. And so I think that's basically what I wanted to say. That's a very quick overview of sort of what PyBaMM is and the sort of ethos of PyBaMM. If you want to get involved, there's loads of ways you can get in touch. We've got an active community on Slack. If you go to, I'll share these slides afterwards, that's a link at the bottom, or you can go to our website and get on our Slack channel. There's lots of useful discussion on there, not just only about PyBaMM, but about battery modeling in general. You can head to our GitHub page where you can create issues or join a discussion board. And again, it's battery modeling chat as well as PyBaMM chat. And we also run implementation type sessions. So if you want to implement something in PyBaMM, get in touch and we can sort of set up some time to go through your ideas and sort of give you pointers about how you can start up using the code. There's a bunch of links there where you can go to our website, follow us on Twitter. We've also got a battery bot. So if you follow @batbot_, It's a bot that tweets random PyBaMM simulations. So if you want those on your timeline, follow that. And yeah, I think that's all I wanted to say. So thanks very much for having me at this session. And yeah, I'll take the questions at the end. Thanks.
Thank you very much for the presentation. It was really informative about the functionality and the use cases and the interesting projects. And I'm really interested about the line pack. We can talk more about that towards the end. So now I'm gonna ask the team at BatteryDev if they can start their presentation.
All right, can you see my slides?
Yes.
Perfect. Okay, great. So welcome everyone. Very happy to see so many of you here today. And I'm also very happy to talk about BatteryDev today. Maybe before we start, let me just briefly introduce the people of BatteryDev that are here today. So we have Anushka Bhutani joining. She's an incoming PhD student in the Viswanathan group at CMU, where she will be mainly working on material informatics. We have Dr. Paul Gasper here, who's a staff scientist at NREL, working a lot with battery testing and machine learning, but also he has a lot of experience with electrochemical impedance spectroscopy. And then there's myself. I'm a PhD student at TU Darmstadt, jointly supervised there, and also at MIT in Boston. And I'm mainly working with battery data analytics, also simulation. Cool. And BatteryDev, let me give you a quick introduction about the competition. So this kind of all started about 1.5 years ago as a completely volunteer-driven project to accelerate battery innovation through open source competitions, because we had the feeling that there is more need for open source in the field. Besides the physics-based approaches, like PyBaMM is a very amazing platform that is out there, but we believe that there is space for more data-driven approaches that are kind of complementary to physics-based simulations. And overall, this whole initiative started by Battery Associates, which is a people-centered and impact-driven battery network and company. They also do a bit of consulting and training, and they also develop an open source battery cycler. Okay, yeah, so really the problem we are trying to attack with BatteryDev is that on the one hand side, what we can see is that there is a scarcity of openly available battery data sets. So this essentially means that right now there are a few initiatives kind of gathering all the academic and testing data that is out there. However, in general, when it comes to field data, there is not much available, and most of the companies, they still face barriers, and they most often don't share the data they have, even though they are large data sets that have been gathered, but they're kept behind the walls of companies. And we believe that actually there are good reasons to share more data to accelerate academic research and also innovation more generally. And then when it comes to open source battery models, I mean, on the one hand side, now we saw PyBaMM, which is a really great example. But when it comes to more data-driven approaches, then they're often very difficult to compare with another. They might have very inconsistent inputs. They might rely on very different things. And also the output and the framing of the problem often differs a lot. And then in the end, what we've been observing is that many companies, they do very similar experiments. There's a lot of work that is kind of repetitively done by different companies out there. And we believe that being a bit more open, sharing more things, especially data that might be a little bit older already, that might not be as relevant in a competitive sense anymore, might really help academia, research, and innovation. And the vision was really to create this 1-week hackathon to bring people together from different disciplines to inspire new collaboration, new approaches, and then ultimately contribute to open source for the community and have more collaborations. A bit of the positioning. So we really thought about, like, it would be nice to bring together people from the traditional machine learning and AI community, with people who are more in research labs, R&D, and also in academia. And in terms of the landscape that is out there, and also a bit the positioning maybe. So the different projects that we've been seeing is, on the one hand side, battery cycling test. So there is software out there which you can use to digitize your data and standardize your data, bring it in a certain format that makes it ready for algorithms and machine learning. On the one hand side, we've been seeing the BEEP framework there. This is from the Toyota Research Institute, has been out there for quite a while. Also, the Galvanalyzer, which is more of a newer project, I would say, has been out there for a year or so. Also kind of taking a similar approach. And then the BatInfo project, which also goes into a similar direction. And in the end, there's Battery Archive, which is really an archive where you can find lots of academic data sets from battery cycling. Then when it comes to battery testing, electrochemical impedance spectroscopy is a very famous testing framework, which is very interesting. We'll be talking about that a bit more later on. Anushka will give an introduction about that. There are two tools out there that currently do different types of EIS analysis, and during BatteryDev, there were a couple of machine learning frameworks developed to deal with EIS data and the challenges associated with them. And then when it comes to battery simulation, we just heard that PyBaMM is like probably the largest framework that is out there in Python. Then there is also a solver for the DFN model, which is called PetLion, which is implemented in Julia, which is a very fast implementation, but doesn't have as many features as PyBaMM. And then also there's a bit older MATLAB implementation, LionSimba. All right, so I hope this kind of gives a bit broad overview about the landscape we're in. And just as a brief history about BatteryDev, we started off in February 2021 with the first competition. We had 33 participants in that first competition. Then we had a second competition in March this year with about 100 participants. This was really amazing. And right now we are in this process of writing up results, and hopefully in a couple of weeks, we'll be able to share some really nice data and some approaches that were applied on this data. And also there's ongoing support needed. So BatteryDev is entirely volunteer driven. So if anyone wants to get involved, feel free to reach out to me or to the BatteryDev team. All right. And maybe just for the framework of the competition this year. So on the one hand side, we were reaching out to companies to give us data. So the goal was really like to collect data from industry for the hackathon that can subsequently be shared openly, and also store that data in a clean and structured way. And then during the competition, the different teams were competing on visualizing the data and also training models on those data sets and making predictions, but also very crucially collaborate with each other in the teams, but also between teams, then evaluate the results, and last publish the results and make them available. And this year, I mean, I'm very happy we had people from 20 countries, 19 teams who had 9 sponsors from industry and academia, and 2 challenges. And today we'll be talking about challenge 1, which is about electrochemical impedance spectroscopy data set, which was provided by QuantumScape. And with that, I will be handing over to Anushka.
So, like Kim said, the first challenge was to do with EIS, or electrochemical impedance spectroscopy. So before we dive into the challenge, I'll just introduce what EIS is for those of you who may not have encountered it before. So EIS, the electrochemical word in it indicates that it's used to study electrochemical systems and processes. So that might be fuel cells, corrosion, or in our case, we were using a data set that was where EIS was used to study batteries. The impedance part of it, so dialing back a bit, I'm sure everyone's familiar with resistance, which is basically the ability of a circuit element to resist the flow of current. But when we speak about resistance, it's only limited to idle resistors, which follow Ohm's law and where the resistance of the element is independent of frequency. So impedance extends that concept and it brings in frequency dependent resistance to current flow of a circuit element. So impedance assumes that an AC current of a specific frequency is applied to that element, and then we measure what the resistance to flow of current is. And this is how we can calculate impedance. So it's equal to the voltage divided by the current. This might look familiar because it's like Ohm's law, except it's extended to AC currents. And then moving on to the final word, spectroscopy. So spectroscopy, because the impedance measurements are repeated over a wide range of frequencies, and that's what gives us ultimately an EIS test. So to understand this a bit better, let's imagine we're making an EIS measurement. So what you would first do is you would apply a small potential of a fixed frequency. You could also apply a small current in practice, but let's just assume it's potential to make this easier. And because this is AC, so it has a sinusoidal form. So that's indicated by the first equation. The potential as a function of time follows a cost function shape. And then you measure the response. So the response also has a sinusoidal shape, but there's a phase shift because of the impedance. And that phase shift is important. So we can calculate the impedance using the formula similar to Ohm's law that I discussed before, divide the potential by the current. And that gives us a magnitude and an angle. So when you have a magnitude and angle, you can represent that as an imaginary number. And that's basically how impedance is represented. So you repeat this same thing over a range of frequencies, and that's how you get an EIS spectrum. So like I said, impedance is an imaginary number. So there's two ways people commonly plot it. So the first is the Bode plot, where the log of the frequency is plotted against the log of the impedance. But here you have two separate lines. One of them is the real impedance and the other is the imaginary impedance. A more common way of doing it is a Nyquist plot, where essentially you plot the real part of the impedance against the imaginary part of the impedance. And in this case, the frequency is implicit because each of these points are taken at a different frequency. And then how do we model EIS data? So one of the common ways of doing this is using equal circuit models. So for example, like the Nyquist plot that we looked at on the last slide comes from an equivalent circuit model that has a resistor and a capacitor in parallel. And these equivalent circuits essentially have the same impedance as whatever you're trying to model. So some other equivalent circuit elements that are commonly used are like an inductor or a CPA element, which is like a capacitor, but it's an imperfect capacitor, which is often more reflective of the reality of electrochemical systems. So in some of these Nyquist plots, you can see the resistor is basically ideal. So it only has real resistance. It's shown here in plot A. So it's just a plot on the x-axis. And then if you connect a resistor and capacitor in series, the resistor leads to like the X translation and the capacitor is a straight line. Resistors and capacitors in parallel give you like the semicircle shape, which is very characteristic of like corrosion or battery or fuel cell EIS plots. So finally coming to the actual BatteryDev EIS challenge. So our challenge statement had two parts. The first part was to do with classification. So given an EIS spectra, you had to come up with a machine learning model, which could tell you what ECM, equivalent circuit model, which best described that EIS spectra. And there were 8, so we gave them 8 possible equivalent circuit models that could be fit to that EIS spectra. That's why it was a classification challenge into 8 different classes. And then the next part was more challenging. It was regression. So given a spectra, you had to come up with what parameters would parameterize the ECM model. So like we saw in the last slide, like moving the different values of resistance or capacitance would result in different shapes in the spectra. And you had to come up with a machine learning model, which would give you a best fit estimate of these circuit parameters. Now Paul's going to talk more about one of the approaches that the teams took to this challenge. and about the data set.
Yeah, so yeah, I'm Paul, and my team, which was also Andrew Sheik from NREL, Risk Goodall, Tushar Desai, and Hugo Leduc won this classification and regression challenge. So one of the cool parts about this data set, but also the challenges of the data set, is that it's quite large in terms of open source impedance data. So there are 10,000 different spectra in the data set. And so here we can see 4 examples of some of the types of impedance that were in the data set, both in the Bode and Nyquist representation. And then QuantumScape had labeled these with the equivalent circuits that they used to fit that data. So extract whatever parameters they were interested in. So we did have like a ground truth, which was the label by QuantumScape, which is always nice to have for a competition. Otherwise, you have to do an unsupervised training. But in this case, we can do a supervised learning problem. So we can go to the next slide. Yeah, here are the 8 different circuits. So we can see that there's kind of 4 different groups of equivalent circuits. There's the LR, RCPE circuits. There's a RCG and RSW circuits, which are both kind of like maybe experiments with blocking electrodes that only have resistance and diffusion components. And then there's a bunch of circuits that are just combinations of RC or RCP elements. Luckily for training, there is fairly balanced across the data set and how much of each class there were, which makes it easier to train a model that has a fair chance at predicting each type of circuit. And then the table on the bottom just has the equations and names of the different shorthands for these equivalent circuit elements if you're unfamiliar with them. So one thing that our team wanted to communicate in how we address this challenge is some common issues with applying machine learning methods just in general, but they're not talked about as much in the scientific field as they are in industry or for like code that's actually sent to a production environment, and that is data leakage. So this is data from QuantumScape, and they, as mentioned, they labeled them with different equivalent. Each file has a different equivalent circuit that they use to model the data, and you can imagine that they probably have certain types of experiments that they're doing. Like I mentioned, the RCGG and the RSWS circuits are probably fit to, for instance, maybe like a solid electrolyte sample with a blocking electrode. And so they have, they have a certain set of experimental parameters for measuring that type of system. And then they use this equivalent circuit model to model that data. So data leakage is this concept of like something inherent to the data could help us predict the circuit, but isn't actually, like a real physical thing we want to model. So for instance, in this data set, we had this insight that there might be different experimental procedures for each different type of circuit. So a common experimental parameter for taking impedance is the range of the frequency that you're recording the data at. And so you can see here that like each circuit does in fact have and actually each circuit has a unique frequency range. So you could actually make almost, with the exception of maybe a few outliers that were recorded at different frequencies, you could make an almost 100% perfect prediction of the circuit model of this data set just by calculating the frequency range. You wouldn't have to know anything about the impedance data you recorded. You could just say that, well, QuantumScape recorded it from 10 hertz to 100,000 hertz, so it's an LR RCP circuit. But obviously that's not scientifically interesting. It's not interesting. It's not an interesting result. We're just learning how QuantumScape recorded their data. So data leakage is something that you can handle every stage from the recording part of your, like actually conducting the experiments all the way to the modeling part. We handle it by data preprocessing. But it's a common issue with machine learning that isn't quite talked about as much in the scientific community as we hope it should be. Next slide. So the next stage of building a machine learning model is often data exploration. So in this case, these are hex bin plots of a reduced dimensional form of the data set. So we're reducing the impedance data down to 2 components, which are shown, the values of those components are shown on the X and Y axis. So basically we're taking the impedance data, which has about 60 columns of 30 different frequencies in the both real and imaginary space, and turning that down into a 2-element vector using a dimensionality reduction technique. And if the impedance was quite easy to tell apart, you'd see that each circuit would have like a very specific bright region on this plot. We can see that a lot of the circuits are actually overlapping quite a bit, which sort of qualitatively makes sense because a lot of the equivalent circuit models are quite similar to each other. And this is just to show, this kind of just proves to us that it's going to be a hard classification problem, because a lot of the data is qualitatively similar to other portions of the data. So it's going to be hard to label them correctly. So the modeling pipeline that we used, and it's definitely not the only approach, was to treat the impedance data as a time series. And there's open source libraries. We use the open source library TS-Fresh, which essentially just grabs features from time series data. It's just it's a publicly available library that will automatically, pull out thousands of possible features from your time series data, and then we push those features into an XGBoost model. XGBoost is a machine learning architecture that's shown a lot of good results on tabular data. So it's kind of like our first baseline. Like we knew it was a tabular data problem, we knew it was a classification problem. So we picked XGBoost, and it was the best result for us, but also the first one we tried. This is just the performance of our model on the test data. So it's trained on approximately 8,000 measurements and tested on 2,000. This is, if you've never seen this before, this is a confusion matrix. So basically along the diagonal is all of the true positives. And then the numbers that are off the diagonal are the misclassified entries where our model is predicting the wrong circuit. And so we can see it's performing quite well. Like most of the boxes on the diagonal have higher values. And then we can also see that, like in the bottom right-hand corner, that there's a group of these RCPE circuits that are all being, they're being misclassified as one another, but we're not confusing, for instance, we're not confusing the RSWS circuit with an RCPE circuit. So that helps us understand that we are pulling out, our model is behaving according to our expectations. Equivalent circuits that we expect to be qualitatively similar are actually being confused more for each other, which makes sense. Next slide. An important part of machine learning is to understand essentially what's happening in your model. So this is a plot of the feature importance by class. So they're colored by the class of the equivalent circuit model. And in this case, we're calculating feature importance using a library, using a method called SHAP, which is one of several different methods you can use to calculate feature importance. And again, the features that are being used to make predictions are being automatically generated by its TS-Fresh library. So we can see, and we can see if these features make sense. So it looks like they're ordered by the average importance across all the classes. So like the most important feature was the number of peaks in the Z imaginary portion of the spectra. And so, from what Anushka showed, a peak in the Z imaginary spectra corresponds to a resistor and a capacitor in parallel. So like each of those RCPE elements in an equivalent circuit should correspond to a relatively obvious peak in the Z imaginary space. And we can see like that immediately is the easiest or the most important feature for classifying almost all of the circuits. And then there's also some other features here, like the fourth and the fourth and the fifth features are kind of the linearity of the data. So, if the data is highly linear across the entire frequency range, that corresponds to a specific type of experiment. Other teams in this challenge tried convolutional neural networks, Bayesian inference approaches, as well as featureizing using the distribution of relaxation times, which is an additional processing step you can do to impedance to try to get insight in the physical processes. Yeah.
All right, thank you so much. Yeah, we won't talk about challenge 2, but there was a challenge 2 for everyone who's interested. Feel free to reach out to ask more about that. And just to finish up, also thanks to the BatteryDev team, to all the amazing people who organized the competition. And with that, we're at the end of our presentation. Many thanks for listening, and we're looking forward to taking questions.
Right, thank you very much for the presentation. So for the Q&A, the members from the audience can just post their question on chat, or they can unmute themselves and ask questions. So let me just start with the first question from Robert Thames. And Robert Thames, the question is, I'm curious about the solvers in PyBaMM. So I have, personally, I've coded my own single particle model, and they take a little bit of longer time depending on how you solve them. So in your documentation, there's a talk about Cassidy solver, which I understand is another open source solver. So I'm just curious why you picked that one, and when would you recommend Cassidy solver? And I understand there are other solvers as well. So what would your recommendations are when using solvers in PyBaMM?
Yeah, sure, that's a good question. So there's a few different solvers available. Which one you use kind of depends a bit on your model. So if you've just got single particle model, that's just ordinary differential equations, not differential algebraic equations. So for that one, you can actually just use like SciPy's integrate solver. The Casadi is actually not a package for doing solvers, really. It's an automatic differentiation package. We actually use it to automatically calculate the Jacobian of any given model. But it just so happens to provide an interface to the Sundial's IDA solver. We've got some other interfaces to that. The reason we end up using the Casadi solver as the default one for DAEs is primarily because it's easier to install than other DAE solvers we found that are interfaced in Python, in the sense that you can just pip install it and it works. We are working on our own interface to Sundial's, an IDA solver, which we're hoping will give us a bit better functionality. I won't go too much into the details, but essentially Casadi was easy to install for like users. But the frustrating thing for us is that we can't believe that no one's written a good DAE solver in Python natively, or at least a decent interface to one. None of them are great, so we're kind of working on our own at the moment. So if anyone in the audience is interested in helping us with that, that'd be really great, because that's something we spend less time on than doing the modeling side of things, I think.
Right. Thank you very much. So all of a sudden we have some questions from the audience. So from Jillian, she's asking, in open source platforms with many contributors or with many different teams competing different approaches, how do you verify that models are correct or as accurate as possible? And this question goes to both PyBaMM and BatteryDev.
I guess I can say something about that first. So most of the models that get implemented, people tend to implement them alongside a paper that they're writing. So in some sense, I guess, you read the paper and decide whether you trust their model. There are sort of a lot of tests that are built in. So when you contribute some code, we've got various different tests that get run against that code to make sure there's a bit of sense checking in there. Obviously, if you're implementing a new piece of physics that's not already in, you'll need to write your own tests for that and sort of convince people that what you're doing is right. But yeah, I mean, the models themselves, like typically the validation in terms of, is the physics correct, comes from the paper that people end up using the code to write. In terms of implementation being correct, hopefully things like the testing catch any bugs in implementation. But also the code being open source itself ends up catching some implementation errors. You know, someone else tries to use it for doing something else and they realize it's wrong. So that's another aspect of sometimes people will put in things that aren't right, but that gets picked up by the community. So it's a little bit self-checking in some respect. But yeah, I mean, all the stuff that goes in gets reviewed. So hopefully, you know, that review process picks up a lot of things. But like any model, you know, you sort of trust whether it's correct or not based on if people can convince you it's correct, whether they've got some comparison to data or whatever else.
That's an unsolicited plug for PyBaMM. Like one of the issues you can have if you're writing your own P2E model is there's a lot of parameters, and normally reading those off of a paper and like, you know, making sure all the units are correct and all the values are correct. Like if you're copy pasting 70 parameters, it's really easy to make a mistake. And P2D models are not super sensitive to the values of all parameters. So it's really quite easy to make a mistake when you're writing your own code that's that complicated with that many hand input values. To make a mistake and not find it out for months or years, or just never find it potentially.
Yeah.
So having it publicly, you know, available, having a lot of eyes, you know, go over those parameters and all the code, like, you know, gives a lot of confidence that the implementation is correct. Obviously, as Robert mentioned, you could add something to PyBaMM and it wouldn't be physically reasonable. But what they have implemented in the library, you know, gives a lot of confidence that, like, well, at least your starting point is sensible.
Yeah, that's a really good
and
point.
Reviewed by a lot of other people before you try it.
Yeah, and there's some nice examples of where, you know, people have found mistakes. So like, yeah, we recently sort of started up this discussion board on our GitHub page where you can go and it's kind of like a forum. And, you know, people say, oh, I was trying to use this degradation model and I was trying to read this paper and there's this factor of 2 I can't figure out. And it turns out there was a factor of 2 missing in the code. And like that kind of thing is just super easy to miss in your own code. And sort of having this community sort of using models can help you pick up these little bugs that are hard to pin down. So yeah, nothing's ever perfect, but hopefully having lots of people look at something helps.
Yes, absolutely. So moving on to another question from Satyam Pancho. So I guess he's asking from BatteryDev. So he asked, so for the BatteryDev people, you only use convolutional neural network and Bayesian regularization method. But what about Levenberg-Manquert method or scale conjugate methods for machine learning? So I guess the question is, why did you use those machine learning algorithms that you mentioned in your presentation?
Yeah, sure. Good question. I can say something about that. So, well, the nature of the competition was really that the teams would pick the approaches they would like to investigate. So we didn't tell them any direction to start off. And the ones we've been seeing were the approaches that were chosen by teams who managed to obtain some results. There are certainly many more approaches you could use on this data that might lead to very good results as well. But just because of the nature of the competition, we ended up presenting the approaches that were picked by the teams.
Yeah, so it was like a hackathon, right? So like it was a week-long competition, but all of us have day jobs. So we don't have 40 hours to work on it. We're trying to fit it on the weekends and after work. So our team's main goal was just to like put in a solution for all the problems. There's the classification problem, and then for every single equivalent circuit, there's a separate regression problem. So like once you identify an equivalent circuit, you want to predict all of the parameters. Can you still hear me? I think okay. Sorry, my mic cut out because I'm in a meeting, I think. But yeah, so our team's approach was, just to use standard libraries for feature extraction and for model architectures to be able to put in the solution to all of the challenges, and then also to address data leakage, to address repeatability and reproducibility. And then someone else had mentioned, like, how do you ensure that the models are accurate. And so all the models in the competition were scored in kind of like in the same fashion that Kaggle competitions are scored, if you're familiar with machine learning, open source machine learning competitions. So basically there was test data held out from the competitors that we never saw. And then our models would have to be able to run on someone else's computer in order to score those competitions. It's really important that to us to just get in a solution that is repeatable and replicable, and then we can submit and then runs on someone else's computer to score on unseen test data.
Right. So
which is I think a bit of a gap in the machine learning implementations in electrochemistry and science in general right now. For instance, there was a seminar last week held by Princeton on reproducibility in machine learning for science, and there were over 1,000 participants. And so just using machine learning tools in a reproducible and replicable manner it's something worth educating about, and the BatteryDev hackathons, I think, really help that push that message in the battery computing.
So there's another machine learning related question from Vipin. So he was asking, can you shed light on a direct correlation on the machine learning models and its relation to the bulk, charge transfer, grain boundary resistance, which is considered as the most common approach while analyzing the data through Nyquist plots?
So we didn't try to do that at all.
Mhm.
Like we didn't try to. So for instance, that's why you fit an equivalent circuit model. For instance, like when you fit an equivalent circuit and then say like this frequency regime is charge transfer, this frequency regime is the porous electrode. Like the mixed diffusion and charge transfer in the porous electrode, this frequency regime is the capacitance of the battery or the solid state diffusion. We didn't do that at all because we're trying to classify 10,000 equivalent circuits. We can't go through and check like get a physical interpretation of every single measurement in 10 hours of work, right? So that's the power of machine learning, is to help us classify these equivalent circuits, and then like later you could maybe go through and say, well, the machine learning says that it's most likely this type of circuit, and use it. I guess the point of the competition wasn't necessarily to like actually fit the data. Like QuantumScape has done that already, but it's more to get a handle on how well machine learning methods can perform with impedance spectroscopy, which is kind of a high-dimensional. It's a high-dimensional form of data, to figure out what are the pros and cons of different approaches, and to again make a replicable machine learning pipeline that addresses data leakage and reproducibility.
Right, thank you very much. So due to the shortness of time, I'm just going to take one more question, or in fact, I'm just going to blend the three questions that I see here with a common theme here. So that question I'll ask Robert Timms is about the battery degradations. So basically, what kind of battery degradation mechanisms can you model in PyBaMM? Quickly, how do you do that? And how do you estimate the parameters of those battery degradation models?
Yeah, good question. So at the minute, they're mostly things to do with interfaces, so things like SEI growth, lithium plating. We have some mechanics in there that can lead to cracking, and that generates surface area and so on. But all the models are continuum-based models. So you've got some ODE or PDE that governs growth of something. So for lithium plating, you've got some extra current density in there that contributes to some side reaction. Parameterizing them is a big challenge. They're very difficult to parameterize. If anyone's got good ideas for that, would be great. I think a lot of the models aren't properly parameterized in the sense of having a detailed parameterization. It's kind of we've got some cycling data, and if we assume it's this mechanism, what parameters give you the right trajectory or something in terms of degradation. So I think that's a big problem, sort of accurately parameterizing these degradation mechanisms, especially when you're not sure which one's actually happening in your cell, right? I mean, you can cycle your cell for ages and then you assume it's one or some combination of mechanisms, but you know, is it actually? So yeah, that's a challenging question, I think.
Yep. So I have a question about LionPack. So it's a library for modeling a pack of batteries. So does it take a long simulation times? And are you have you considered using reduced order models for the LionPack?
Yeah, so it depends on the size of the pack, obviously. If you have a very large pack, the simulation time is quite large. So one approach we're looking at to reduce that simulation time is sort of parallelizing that computation, and that's what Oak Ridge National Lab have been helping us with a bit. In terms of the models you use, so the idea with LionPack is you can drop in any PyBaMM model you like. So that could be a reduced order model. So, you know, you could run a pack simulation with a DFN as every cell. You could run a pack simulation with SPM as every cell. You could run a pack simulation with something even simpler. And that's something that we think is quite powerful in terms of using PyBaMM in a pack simulation, is that you can sort of turn that dial on how complex is my individual cell model within that pack. Sort of understand what you need. And you know, the sort of thing we're thinking about with LionPack is, you know, if I've got some physics-based model for my cells, what happens if I say take some parameters and draw them from a distribution amongst these different cells, different packs, to sort of maybe quantify what's the effect of cell-to-cell variability in a pack and things like that. But hopefully using the physics-based model gives you a bit of control and insight over that kind of interaction.
So as a follow-up, is there thermal variation in temperature in the battery pack that you're considering for LionPack?
So it's either under development or is done to a basic sense. I can't remember off the top of my head, but yeah, essentially, I think at the moment it's set up so that each cell just has some heat loss that you specify differently, but the thermal connections between the cells aren't set up properly at the moment. I think that's still under development, but it's either happening or will happen shortly. I can't remember.
Right, thank you very much. So just for the respect of time for our presenters, I'm gonna conclude this meeting, this event. But because if we go with the questions, like it's gonna take another hour, I'm assuming. So thank you I thank all the presenters for being here, and as well as the audience member for joining us for this event. Thank you very, very much, everyone.
Great, thanks very much for having me.
Yeah, thanks very much for inviting us, and also feel free to share our contacts with the recording so people can reach out if they're interested in anything.
Oh, absolutely. Thanks for your time, and I will share the contact information with our audience so they can contact you or help you with the collaborations and whatnot.
Thanks for having us.
No problem. Thank you for being here.
Cool. Great, thanks, bye.
Bye, everyone.